Bismillahirrahmanirrahim. In our last classes, we discussed about the electrostatic fields. We discussed about the sources of electrostatic field. We talked about the laws that can be experimentally used to determine the electric field intensity at a point due to different sources. In today's class, we will discuss about the magnetic field. We will discuss about the sources that are used to create the magnetic field. What are the sources of magnetic field? How can we determine the magnetic field intensity at a point? So today we will discuss about the Biot-Savart law. The source of steady magnetic field may be a permanent magnet, an electric field changing linearly with time, or a direct current. We shall largely ignore the permanent magnet and save the time varying electric field for a later discussion. Our present relationships will concern the magnetic field produced by a differential DC element in free space. So, a steady magnetic field may be produced by a permanent magnet, an electric field changing linearly with time, or a direct current. So, now we will discuss about the magnetic field that is being produced by a differential DC element in free space. We may think of this differential current element as a vanishingly small section of a current carrying filamentary conductor, where a filamentary conductor is the limiting case of a cylindrical conductor of circular cross section as the radius approaches 0. We assume a current I flowing in a different vector length of the filament dl. So according to the Biot-Savart law, the law of Biot-Savart then states that at any point P, the magnitude of the magnetic field intensity produced by the differential element is proportional to the product of the current, the magnitude of the differential length, and the sine of the angle lying between the filament and a line connecting the filament to the point P at which the field is desired. So according to Biot-Savart law, we have a filamentary conductor and we are assuming a differential portion, a small portion of the filamentary conductor. We are assuming a differential current element of length dl1. Let's suppose this differential current element is at point 1 and the magnetic field intensity is desired to be found at point P, which is actually point 2. So according to Biot-Savart law, what will be the magnetic field intensity at this point due to this differential current element? So the Biot-Savart law states that the magnetic field intensity at point P is directly proportional to the product of the current and the magnitude of the differential current element dl and the sine of the angle lying between the differential current element and the line joining the differential current element to the point P. I am repeating it again. According to Biot-Savart law, the magnetic field intensity at point P is directly proportional to the product of the current, the magnitude of the differential current element dl, and the sine of the angle lying between the differential current element and the line joining the differential current element and the point P at which we want to find the magnetic field intensity. So the sign of this angle. Similarly, the magnetic field intensity at point P is inversely proportional to the square of the distance from the differential current element to the point P. So, at point P, the magnitude of the magnetic field intensity produced by the differential current element is proportional to the product of the current, the magnitude of the differential length, and the sine of the angle lying between the filament and a line connecting the filament to the point P. The line connecting the filament to the point P. So this is actually this angle, and we will take its sine at which the field is desired. Also, the magnitude of the magnetic field intensity is inversely proportional to the square of the distance from the differential element to the point P. The square of the distance from the differential element to the point P. The direction of the magnetic field intensity is normal to the plane containing the differential element and the line drawn from the filament to the point P. So the direction of the magnetic field intensity will be normal to this plane. So the direction of the magnetic field intensity will be normal to this plane, the plane containing the differential element and the line joining the filament with point P. So this filament and this line is actually making a plane. So the direction of magnetic field intensity at this point will actually be normal to this plane. Now we have two normals. We have one normal and we have the second normal. We have one normal and we have the second normal. So which normal will we take? Of the two possible normals, that one is to be chosen which is in the direction of progress of a right-handed screw turned from DL through the smaller angle to the line from the filament to point P. So we will use this smaller angle, and if we take a right-handed screw, so our direction will be this one. If we take a right-handed screw here and we use this small angle from this filament to the line, so which one will be our direction? This one. So that will be actually the direction of the magnetic field intensity. Using rationalized MKS units, the constant of proportionality is 1 by 4 pi. So the Biot-Savart law described above in some 150 words may be written concisely using the vector notation as dH. The magnetic field intensity will be equal to I dl cross AR divided by 4 pi epsilon 4 pi r square. Now here we have taken the cross product, because this is actually the vector notation, so that is why we have taken the cross product. If we use the magnitude of the magnetic field intensity, so it will be equal to I dl sine theta divided by 4 pi r square. That will actually be the magnitude of the differential magnetic field intensity at point P. But here actually we are representing this magnetic field intensity in vector notation. So here we will take the cross product with its unit vector, because we know that the magnitude of a unit vector is actually unity. So if I take IDL cross AR, so its magnitude will be equal to the magnitude of DIDL into the magnitude of AR into the sine of the angle between them. So the magnitude of AR is actually unity. So we will get IDL sine theta divided by 4 pi r square. Now if we represent it in terms of its vector, so we know that the unit vector is the vector divided by its magnitude. So we will get IDL cross r divided by 4 pi r cube. The units of the magnetic field intensity H are evidently amperes per meter. The geometry is illustrated in figure 8.1. We have already discussed this geometry. If we locate the current element 8.1, if we locate the current element 8.1 and describe the point P at which the field is to be determined as point 2. It means that point 2 is the point at which we want to find the magnetic field intensity. Then dH2, the magnetic field intensity at point 2, will be equal to I1 dL1 cross AR12. I1 dL1 cross AR12, that is actually the unit vector of the vector joining the differential element and the point P. So this is actually the vector R12 and its unit vector is AR12 divided by 4 pi R12 whole square, the magnitude of the vector. The law of Biot-Savart is sometimes called Ampere's law for the current element, but we will use the term Biot-Savart law because if we use the term Ampere's law for the current element, it may be confused with the Ampere's circuital law, which we will discuss later. So the law of Biot-Savart is sometimes called Ampere's law for the current element, but we shall retain the former name because of the possible confusion with Ampere's circuital law, to be discussed later. In some aspects, the Biot-Savart law is reminiscent of Coulomb's law when that law is written for the differential element of charge. It means that there is some sort of similarity between the Biot-Savart law and the Coulomb's law. Both shows an inverse square law dependence. If we talk about the differential electric field intensity at a point, so both shows the inverse square relationship, and both show a linear relationship between the source and the field. Between the source and the field, the chief difference appears in the direction of the electric field, because the chief difference appears in the direction of the field because the electric field intensity is along the direction of the force, is parallel to the force. Similarly, the magnetic field intensity is perpendicular to the plane, to the force which is acting by the differential current element. So the direction of the electric field intensity is parallel, whereas the direction of the magnetic field intensity is perpendicular to the plane containing the source and the field point. It is impossible to check experimentally the law of Biot-Savart as expressed by 1 or 2 because the differential current element cannot be isolated. But remember that we can check the integral form of Biot-Savart. We cannot check the differential form because the differential current element cannot be isolated from a filamentary conductor, and we have restricted our attention to the direct currents only. So the charge density will not be a function of time, as we are talking about the direct currents. So the charge density will not vary with time. The charge density will not be a function of time. When the volume charge density is not a function of time, so according to the continuity equation, we know that the divergence of the current density will be equal to the negative rate of change of the volume charge density. And in this case, the volume charge density is not a function of time, so the divergence of J will be equal to 0. And upon applying the divergence theorem, so we will get the closed surface integral of the current density will always be equal to 0. It means that the total current crossing any closed surface is 0. and this condition may be satisfied only by assuming a current flow around a closed path. When a current is flowing around a closed path, so the total current crossing any closed surface will be 0. So it is this current flowing in a closed circuit which must be our experimental source, not the differential element, because we cannot isolate the differential element from the filamentary conductor. So it is actually this current flowing in a closed circuit which must be our experimental source. So now here we can write the integral form of Biot-Savart law. So it follows only that the integral form of the Biot-Savart law can be verified experimentally. This is actually the integral form of the Biot-Savart law. Equation 1 or 2 of course leads directly to the integral form, but other differential expressions also yield the same integral formulation. It means that this integral equation can be derived directly from equation 1 or 2, from this equation or this equation, but actually other equations may also yield the same integral formulation. Any term may be added to one whose integral around a closed path is 0, like the conservative field. That is, any conservative field could be added to 1. The gradient of any scalar field always yields to a conservative field, and we could therefore add a term, the gradient of G, to 1, where G is a general scalar field, without changing 3 in slightest. This qualification on 1 or 2 is mentioned to show that if we later ask some foolish questions not subject to any experimental check concerning the force exerted by one differential current element on another, we should expect foolish answers. So this was all about the Biot-Savart law. If you have any question, please write them down and you can ask anytime. Thank you.